All of you. Yeah, this is a lecture number 6 in a heat and mass transfer subject. In previous lecture we have finished heat transfer through a fin, heat transfer through a plane wall, and heat transfer through a cylinder. So today in this lecture number 6 we will talk about the numerical problem based on conduction. It may be a plane wall or it may be a cylindrical form and a spherical form. So let's first numerical problem, which is based on a composite wall. So calculate the rate of heat loss through the vertical walls of a boiler furnace of size 4 meter by 3 meter by 3 meter high. The wall are constructed from an inner fire brick wall 25 centimeter thick of thermal conductivity 0.4 watt per meter Kelvin, a layer of ceramic blanket insulation of thermal conductivity 0.2 watt per meter Kelvin and 8 centimeter thick, and a steel protected layer of thermal conductivity 55 watt per meter Kelvin and 2 millimeter thick. The inside temperature of the fire break layer was measured at 600 degree centigrade, and the temperature of the outside of the insulation is 60 degree centigrade. So find out the interface temperature of the layer. So this problem is related to the composite wall having 3 layers, the layer 1, layer 2, layer 3, made by number 1 fire brick, number 2 ceramic blanket, and number 3 steel protective. So these layers are in a series connection. So the given data as per length L is equal to 4, B is equal to 3 meter, and H is equal to 3 meter. Therefore the area of the rectangular wall, this is 4 multiplied by 3, is equal to 12 millimeter square. So this is a special case of series connection wall. In that case the area of the each wall will remain same, and it is equal to 12 watt per 12 meter square. The next is, in case of fire brick, the thickness of the fire brick is given by 25 centimeter, and the conductivity is also given 0.4 watt per meter Kelvin. In case of steel wall, the thickness of the steel wall is equal to 0.02 meter, and the conductivity of the steel wall is 54 watt per meter Kelvin. And the last layer is made by insulation having a thickness of 0.08 meter and conductivity 0.2 watt per meter Kelvin. These are the given data, and the high temperature, the inner temperature of the wall, that is denoted by T1, is equal to 600 degrees centigrade, and the last temperature, or we can say the lower temperature of this composite slab, is given by a 60 degree centigrade. So in that case we have to calculate the interface temperature of the layer. It means the temperature between 1 and 2 wall, the temperature in between 2 and 3 wall. So these are the numerical problem which is based on a composite wall. So let us start. This diagram, it is shown that these walls are connected in a series pattern. Therefore the resistance of each wall is R1, R2, R3. R1 stands for plane wall 1, R2 stands for plane wall 2, and R3 stands for plane wall 3, where 1, 2 and 3 represented by fire brick, insulation and steel. So let us assume the temperature between the 1 and 2 wall is T2, and the temperature between the 2 and 3 wall is T3. These are the unknown value, but in this problem T1 and T2, T4 are given. T1 is a high temperature and T4 is a lower temperature of this system. So T1 is equal to 600 degrees centigrade and T4 is equal to 60 degrees centigrade. In that problem we have to calculate, number one, the total rate of heat loss from this system, from this wall, and we have to also find out the difference of T3 minus T4. So the Fourier law stands for a plane wall, that is the heat loss, that is Q is equal to delta T overall divided by the summation of the total thermal resistance. So delta T stands is equal to T1 minus T4, and this is 600 degrees centigrade minus 60 degrees centigrade. So where the summation of R is a summation of R1 plus R2 plus R3, where R1 is equal to L1 divided by K1 A1, and R2 is equal to L2 divided by K2 A2, and R3 is equal to L3 divided by K3 A3, where A1, A2, A3 are equal and it is equal to 12 meter square, where L1, L2, L3 are the thickness of each layer, and K1, K2, K3 are the conductivity of the each layer. So putting the values of L1, K1, A1 in equation R1, R2, R3, we get R1 is equal to 0.0521 watt per meter Kelvin, R2 is equal to 0.0333 Kelvin per watt, and R3 is equal to 0.000031 Kelvin per watt. Therefore the rate of heat loss, this is Q is equal to T2 minus T4 divided by RT1 plus RT2 plus RT3. In that case we always assume that this is a steady state heat transfer rate. So therefore the heat loss between the slab 1 should be equal to the heat loss between the slab 2 and the heat loss between the slab 3. These are equal. So we can say Q1 for 1 wall, Q2 for Q2 wall, and Q3 for 3 wall are equal. Therefore Q1 is equal to Q2 is equal to Q3 is equal to Q is equal to T1 minus T4 divided by the total summation of resistance. So putting the values of T1 and T4 and R1, R2, R3, we get the final answer. This is Q is equal to 600 minus 60 divided by 0.0521 plus 0.000031 plus 0.0333, and the final answer is that is heat transfer rate from this system is 6320.96 watt or 6320 watt. This is the final answer. And in this problem we also find out the temperature drop across the steel layer between 2 and 3. So T2 and T3 are the interface temperature between the layer of 1 and 2 and the layer of 2 and 3. So Q is equal to T2 minus T3 divided by resistance of RTH3, because R1 is equal to R2 is equal to R3, as we have already assumed that this is a case of steady state. So therefore the Q1 is equal to Q2 is equal to Q3 by putting the values of Q and RTH in this equation. So therefore the final results are obtained. T3 minus T4 is equal to 0.0196 Kelvin. So these are the results of this problem. In this problem we have to find out, number one, the overall heat loss and the temperature drop between the two layers. So the next related to conduction, and in this problem we have considered a spherical container. So the question is, a spherical container of negligible thickness holding a hot fluid at 140 degree centigrade and having an outer dia of 0.4 meter is insulated with 3 layers of each 50 millimeter thick insulation of K1 is equal to 0.02, K2 is equal to 0.06 and K3 is equal to 0.16 watt per meter Kelvin. Starting from inside, the outside surface temperature is 30 degrees centigrade. Determine, number first, the heat loss, and second part is interface temperature of the insulating layer. So this is a problem which is related to a spherical container. So the given data are, the outer diameter is 0.4 meter, therefore the radius is 0.2 meter. the radius of outer surface, this is R2, is equal to R1 plus thickness of insulation of first layer. Therefore, the R2 is equal to 0.2 plus 0.05, and the final answer R2 is equal to 0.25 meter, and the outer layer, the final layer of the spherical is R3 and R4. R3 is equal to R2 plus thickness of second insulation, and it is equal to 0.25 plus 0.05, and the value of R3 is equal to 0.3 meter, and the last one value R4 is equal to R3 plus thickness of third insulation, and it is equal to 0.3 plus 0.5, and R4 is equal to 0.35 meter. So this is a case of a composite spherical container having a layer of R1, R2, R3 and R4, and the final temperature and the initial temperatures are given as THF is equal to 140 degree centigrade and TCF is equal to 30 degree centigrade, or we can say THF stands for hot fluid, या T hot fluid, या temperature of the hot fluid is equal to 140 degree centigrade, and the temperature of the cold fluid is 30 degree centigrade, and the last given values is K1, K2, K3, because this cylinder is a spherical container is a composite container. So having conductivities are K1, K2, K3, and 0.02 watt per meter Kelvin, 0.06 watt per meter Kelvin, and 0.16 watt per meter Kelvin respectively. So let us start the solution. T3 is equal to T2 minus Q times of RTS2, and T2 is equal to 132.71 minus 91.62 multiplied by 0.8842, and the last answer is T3 is equal to 35.09 degree centigrade. So T2 and T3 are the interface temperature, and T2 is always greater than T3. As we have seen, T2 is equal to 54 degree centigrade and T3 is equal to 35 degree centigrade. So this is a problem which is related to the composite spherical container. Related to the steel tubes, the question is a steel tube with 5 cm inner diameter, 7.6 cm outer diameter, and thermal conductivity K 15 watt per meter degree centigrade is covered with an insulation covering of 2 cm and conductivity 0.2 watt per meter degree centigrade, hot gases at 330 degree centigrade with overall heat transfer coefficient 440 watt per meter square degree centigrade flowing inside the tube. The outer surface of the insulation is exposed to cooler air at 30 degree centigrade, which with H is equal to 60 watt per meter square degree centigrade. Calculate the heat loss from the tube to the air of 10 meter of the tube, and the temperature drop resulting from in thermal resistance of the hot gas flow, the steel tube, the insulation layer and the outside layer. So the given data are the inside diameter, this is D1 is equal to 5 cm and convert into meter, it is equal to 0.05 meter, but the radius is D1 by 2, or R1 is equal to 0.025 meter. The outer diameter of the steel tube is 7.6 cm, or it convert in meter, that is 0.076 meter, and the outer radius is D2 by 2 and it is equal to the 0.025 meter. Therefore the radius of R3, the radius R3 is equal to R2 plus the thickness of insulation, so it is equal to 0.038 plus the 0.02 meter. So the next value, the thermal conductivity of the steel, that is K1 is equal to 15 watt per meter degree centigrade. The thermal conductivity of the insulation, that is K2 is equal to 0.2 watt per meter degree centigrade, and the hot gas temperature, this is THF denoted by THF suffix HF is equal to 33 degree centigrade plus 273, it is equal to 603 Kelvin. The heat transfer coefficient inside is equal to 400 watt per meter square degree centigrade. The ambient air temperature, this is TCF, is 30 plus 273 and is equal to 303 Kelvin. and the last value is the heat transfer coefficient of the outer side surface is 60 watt per meter degree centigrade. So in this problem we have to find out number one, heat loss and the temperature drop between the surfaces. This is THF minus T1, T1 minus T2, T2 minus T3 and T3 minus TCF. So let us start the solution. So we know that the overall heat loss, this is Q is equal to T overall divided by the total summation of thermal resistance. In that case there are three layers, so which are connected in series manner. So the formula of heat transfer rate through the composite cylinder is equal to R is equal to 1 upon 2 pi L multiplied by 1 by HHF R1 plus 1 by K1 ln R2 by R1 plus 1 by K2 ln R3 by R2 plus 1 by K3 ln R4 by R3 plus 1 upon HCF R4. So putting all these value in this equation, we get the final answer of the heat loss through the composite cylinder, and the final answer is Q is equal to 7451.72 watt. Very important. This problem is a mixture of series connection and parallel connection. In this problem, these A, D and E walls are connected in a series manner, but B and C walls are connected in a parallel pattern. So this is a mixed problem in which some walls are connected in series and some walls are connected in parallel manner. So the question is, determine the heat transfer through the composite wall as shown in the figure. Take the conductivities of A, B, C, D, E as 50, 10, 6.67, 20 and 30 watt per meter Kelvin respectively, and assume one dimensional heat transfer. Take the area of A, D, E is equal to 1 meter square and BC is equal to 0.5 meter square, and temperature entering the wall is 800 degree centigrade and the leaving at wall is 100 degree centigrade. So in this case, A, D and E are the three wall having same areas as given in the problem. This is equal to 1 meter square. The area of the B and C wall is 0.5 meter square, and the temperature at this side, we assume this is the inner side and we assume this is the outer side. The hot gases is entering through A and leaving the E side. So the hot temperature, or we can say the initial temperature, the highest temperature of the system is 800 degree centigrade at this side, and the lowest temperature of the system is at C side and E side. So Ti is represented in inner surface temperature. T naught is equal to T naught represented the outer surface temperature, or 800 degree centigrade is this side temperature and 100 degree centigrade is this side temperature. K, Kb, Kc, Kd, Ke are the thermal conductivities of the different walls, and areas are equal in AA, AD, AE, and AB, AC are equal, and it is equal to 0.5 meter square. In this case we have to find out the heat transfer rate. So let us start. The plane wall B and C are in parallel connection. So in that case the total value of resistance, this is RT is equal to 1 by RTHB plus 1 by RTHC. Therefore solving this equation, RTHB plus RTHC divided by RTH into RTHC, but RTH1 and RTHA is equal to LA divided by KA, where LA and KA are the length and conductivities of the A wall. So RTH2 is equal to RTHB, RTHC divided by RTHB plus RTHC. RTHB is equal to LB divided by KB to AB, and RTHC is equal to LC divided by KCAC, where KCAC are the conductivities, and RTH4 is equal to RTHE is equal to LE divided by KEAE. R3 is equal to RTSD is equal to LD divided by KDAD. Putting the values of LA, LB, LC, LD, KA, KB, KC, KD, so we get the results of RTH1, that is RTHA is equal to 0.02 watt per Kelvin per watt. HB is equal to 0.02 Kelvin per watt, RTSC is equal to 0.0969 Kelvin per watt, and the final is RTSD is equal to 0.05 Kelvin per watt. Or putting all these values in our general equation, this is Q overall is equal to THI minus TH naught divided by summation of total resistance. Thi is equal to 800, Th naught is equal to 100 degree centigrade, and our summation of RTH is equal to RTH A, B, C, D, and final answer is 3137 watt. So today in this lecture number 6 we have covered a numerical problem which is based on number first, heat transfer through a composite wall, heat transfer through a spherical wall, heat transfer through a composite cylinder, and the last one is heat transfer through a series connection and parallel connection problem. So thank you.